We will look at paleoclimate observations here and then return to mechanisms a little bit more later on when we look at the patterns of warming and natural variability and so on. So this is a great observation from Vostok ice core over Antarctica. We won't go terribly deep into details of how such data are generated, but glaciers are built, as I said before, basically by snow falling on land and not melting because it's so cold. More snow falls on top next year, and when that happens, air bubbles get trapped with all the signatures of amounts of dust and CO2 and methane and N2O and so on. And as snow keeps falling, it gets compressed and gets converted into glaciers, which are different than ice, as I said, because glaciers can get several kilometers thick and can flow under their own weight like molasses, like rheology, especially when they are on a slope like a mountain, because mountains favor collecting snowfall and keeping it and building glaciers. Of course, large flat continent like Greenland and Antarctica can also collect snow and ice if they are cold enough, right? So what is being shown here is essentially the CO2 change. You can see that it's going from about 190 ppm by volume to about 260, and then back down to about 180, and so on and so forth. But you can clearly see that this phase is very abrupt, quite rapid compared to this phase. Slightly different here, but you can still see these sawtooth pattern. And surprisingly, there is a very coherent signature in temperature that matches a similar shape, and also in methane. Okay, so what's happening is that the orbital forcing, changes in obliquity, precession, and ellipticity are creating energy balance perturbations, which then are amplified by internal feedbacks, the most critical one of which is the ice albedo feedback. What is ice albedo feedback? Basically, if radiation, let's say at 65 north, which is kind of a critical latitude for initiating glacier formation or glacier melt, let's say it changes because of orbital forcing. Let's say it gets warmer, and if there is a glacier mass, it may start to melt the glacier. Glacier and snow have very high reflectivity or albedo, so they lose a lot of the energy and help global temperatures be cooler. But if glacier melts, then the albedo is decreased, more energy is absorbed, temperatures get warmer, and more glaciers melt. So this process can go very rapidly once initiated, as you can see in these phases where temperatures are changing by several degrees over a few thousand years, and we'll see an example where this can happen even on a decadal time scale, with some blips happening on less than a decadal period. Okay. And when glacier builds, there are various ways in which CO2 gets trapped into the ocean, on land, and so on. And when glacier melts, all that CO2 is re-released. So you can see that there is a cycle of CO2 happening. So in the past, when human beings were not around and everything was happening because of internal feedbacks and perturbations from orbital forcing or continental movement, for example, temperature would show the first signal of change, and then glacier mass would begin to change, and then CO2 and methane would change. So we can't see it very clearly here, but actually temperature leads. My apartment is being cleaned and he keeps making a lot of noise. So temperature leads and CO2 and methane follow. Whereas what we are doing now is we are increasing methane and CO2. Okay, so CO2 has gone from let's say here at 280 ppm before industrial revolution to now we are almost over 415, and methane is somewhere around I think 1900 or 2000. The temperature has warmed by about 1.1 or 1.2 degrees over the same period because we are still in a transient response. The heat, additional energy being trapped by greenhouse gases is going into the ocean, going into melting glaciers, and it's not showing up yet as atmospheric warming. Ocean takes up more than 90% of the additional energy from greenhouse effects. Anthropogenic greenhouse gas increases. So these are the asymmetries we have to remember in the ice albedo feedback. This side where it's changing slowly over 100,000 year time scale is because if orbital change forces a reduction in energy and cooling and glacier grows, then albedo increases, more energy is lost, further cooling happens. But as cooling happens, atmosphere gets drier because cold atmosphere holds much less moisture. So the snowfall rates which build the glaciers begin to decrease, and basically Antarctica and Greenland are deserts. They get about 20 centimeters of rain per year compared to the average of 1 meter per year over the rest of the world. So this is why building glacier becomes slower and slower as temperatures get colder and colder. Both are positive feedback, so once you trigger them, they go in the same direction. Very fast in this phase and very slow in this phase. So both ice glacier building and glacier loss are ice albedo feedbacks which are positive. One is going in the warming phase and one is going in the cooling phase. Okay, these are critical things to remember. So that we have to keep in mind. We will come to the other concept of committed warming, which is essentially what we implied here. We have increased the greenhouse gases because of our activities, but the warming is still catching up. And because CO2 has a very long residence time in the atmosphere of decades to centuries to even millennia in some cases, the warming will continue even if we just cap off all the emissions right now, because we have already accumulated carbon since industrial revolution, going from 280 ppm to over 400 already. So that is the committed warming that we have to watch out for, unless we begin to take out the carbon dioxide from the atmosphere and begin to put it somewhere within the ground or within the ocean and so on. So we'll talk about carbon capture and sequestration later on, but these are the ice albedo feedbacks that are very critical. We'll come back to other time scales a little bit later on, but this focus here is mostly on observations. So these kinds of observations at various time scales come from ice cores. There are shorter time scales from speleothems, from ocean sediment cores, tree rings, corals, and so on. Okay.